The next speaker is Hugo Sanchez. He's also a PhD candidate at the Hochschule Anhalt in Köthen in Germany. And also he works on the field of solar modeling. Hugo, please.
Well, it's my pleasure. Thank you so much for the kind introduction. I think I choose a complex name for what I hope is not a complex presentation. So please follow me in this journey. My name is Hugo Sanchez, and I'm also talking about on behalf of my co-authors. Without them, there would be not possible to work. So this is the outline that I want to present today. Actually, I just split it like in 3 main questions and then some conclusions and open work, because this is what we have. At the end of the day, more questions than answers, but this is science. So first one, I want to start to saying why we are doing that. Then we just try to compare some ray tracing tools in order to measure the accuracy on the irradiance on the ground. Third, we have to go how far do we need to go in the resolution terms, because this is an important topic that was explained by my colleague before, and then we just open some conclusions and work. Okay, now the first motivation is why we are doing this. Typically, and this is part of the conference, that's why it's UPV6, so basically we have our solar resource, and we have the solar module, and then we have the solar production. We are already well known how to do it, so there's still a lot of improvement, but this part is coming out. Nevertheless, there are coming emerging applications, such as crops under the models, and then that's why it's important to understand what is the real effect that we have. Okay, yesterday there was a really nice discussion about social acceptance in the agrivoltaics and its novelty sites. But to be perfectly honest and true, if we want people to adopt this technology, specifically the farmers or the landowners, this is also about the profitability of the system. In that case, we need to assure that our planning tools that we are using could give us accurate systems in terms of energy production and crop production in that way. So that's why the focus of this research will go into the irradiance into the ground, basically because there was not well explored by the moment to understand what is going to happen over there. And actually, this is the first step, because if we have accurate irradiance in the ground, it will be possible also to go forward for more physical analysis in terms of the microclimates, and also to understand the crop production, or as well explained by my colleague before, in terms of crop protection and other things. The main point of this, and then try to close the circle, is the economical estimation, or the tools, and then the adoption for that will be hardly depends on the accuracy or how good or bad could be these tools. So the first step to analyze the feasibility of agrivoltaic systems will be, or begins with an accurate light assessment. So that drives us to the first question. So we use ray tracing in that case due to the capabilities that were explored by my previous colleague in terms of the study of complex scenarios, specifically when we have complex structure and so on. So this is the methodology that we are using. So first, in our flow diagram, we just get in the meteorological data for simulation, normal. Then we also use transposition models to go in terms of the irradiance that we could have in the system, considering albedo, the composition, and so on. And third one, we just start bashing the 3D system model. So as you see here, and we'll explain the experiment later, so it's try to get some complex structure, and at the end of the day, try to reach into the calculation of the irradiance in the ground. Because the money that we could get in terms of the crops will be started according to the irradiance that we could have in the ground, because as well was well exposed in the morning. So basically, the photosynthetic rate that we could have into the crops will be depending on the irradiance. It's not that simple like that. The complex becomes more problem. But anyway, this is the first step. So for this analysis, we use a couple of tools. The tools PESA that was developed by our colleagues from Liège University. And on Tuesday, we have a presentation from Professor Lugo from Liège University that explains all the framework and may see the main aims and the goals. And then we are also comparing bifacial irradiance. Both of them are open source, so there's open opportunities to keep collaborating, to analyze, and to make studies. And basically, they are quite similar. So in this case, PACE, the Python agrivoltaics simulation environment, is well adapted for agrivoltaics. Bifacial irradiance is well used in the terms of PV. Both of them are open source. The repositories are there, so this is what we take advantage of that. So the first step that we make is just to try to make the validation. Okay? Typically, in a solar radiation, we just try to see the irradiance that we can reach into the model. And this is quite correct. There's a lot of work over there. Nevertheless, if we want to see how important could be the crops into the system, we have to going beyond the models in that case. So in this experiment, we just place a couple of sensors. So the first one is just a global horizontal irradiance sensor in yellow, and then in blue, we just put a sensor below the models under this complex structure that we have. So basically, we have a space in between the models, and then just in the middle of them, we just get some values. So we just receive the data, we put this data as an input, and then we just run the simulation. So as the first result, there was kind of high resolution data, 15 minutes. So yeah, nevertheless, good resolution data, let's say. And this is the results that we have it, okay? So this is an invitation to read the paper. In the paper, we have more data and more cases, but I choose the clear sky model because in terms of shadow and irradiance in the ground, when we have more irradiance or clear sky models, this is more complex to simulate the shadow because at the end of the day, we can reduce the problem that when we have a lot of diffuse radiation, is basically the same. So there's not a big difference between two of them, and that's actually we already saw it. So actually, we just reached like a small underestimations. Somehow, both algorithms are a little bit shy in order to estimate the sensors. So basically, in yellow, you have the global horizontal irradiance that we have basically a perfect day. It was a really nice summer day. And then in red and purple, do we have the simulation and the comparison of the two of the software. So actually, the effect that we found into the bifacial radiance will lead me into a second question. But before passing through that, let's just make a small comparison, right? So this is basically the main statistical analysis that we make. And as a first conclusion, we have said that these both tools can reach us into accuracy between 2 and 5%. That again, if I was talking about the irradiance or the normal simulation for a PV model, maybe it's not acceptable. But this is a first try to make the irradiance into the ground, into the complex scenario. So there's a lot of opportunity to working over there. But nevertheless, we can assume that this is acceptable by this moment. And I will explain you a little bit agronomical aspects after that. So try to understand from where is coming these uncertainties. Then the second question is how far we can go into the simulation. So my colleague previously explained that ray tracing or low resolution or no rendering ray tracing techniques takes not that much time, but nevertheless, we can make it as complex as possible in that case. And how much resolution do we need? So in that case, we just try to make a sensitivity analysis into the renderization of the image on the ground. So basically, we just have a calculation. So we just get a map of irradiance into the ground, and then we just start increasing the discretization matrix that we will have. So we just run from 5 sensors up to almost 500 sensors in that case, so just to make the calculation and to see what is the performance and maybe the misbehavior of these traps. So basically, ray tracing is an accumulative, it's a matrix calculation, so we just go sensor by sensor counting in that case. So as far as we go with sensors, we just increase the capability computational. So my colleague is right, so the times for simulation is not that long, so as you see in the performance of the radio. So in that case, we measure the time performing, and also we measure the memory. And this is quite important. For back ray tracing, low resolution, we are not even using the GPU. We're just using the set size memory that is part of the RAM. So basically, with a normal laptop, you can run this kind of algorithm in that case. Then in green, this is what you see, the memory changes that we could have into the computational side. And basically, it becomes about the resolution. And then in one point, we just start getting some uncertainties of the solution. So the first one is when we reach around 50 sensors matrix. So basically, this is a normal computational side. And then the second 2 points is just a zoom of the figure. So we just start getting more resolution. But what happened in that case? If we want to go for more resolution, then we just creating a more bigger gradient. So because in the first case, it's just black and white. But later, we just start making a gray scale for many points. And these many points can drive us into some uncertainties. Even when we start reaching, and then we just make this peak in the memory consumption, then we have a more variety of the system. The real question is, do we really need such much precision in that case? And then the question, and don't forget the motivation, we try to provide tools to the farmers and the stakeholders in such a way that they can use it for the future. So if we just try to understand what the farmer needs, it's about they just need make nice plotting, and then actually this is a really open question right now in terms of the optimization of the system. So how far could we go? But at the end of the day, maybe go into a smaller accuracy is maybe not efficient, because at the end of the day, we are going to make a tool that will be not useful. So at the end of the day, maybe a farmer, what we need is just a small tool that can provide some assessment in that case, and then they provide the system. So for example, when you see all the crop modeling that we have, all this crop modeling is just got in square meters. So there's not going small. It's a really nice academic exercise, but maybe it's not that useful at the end of the day, because a farmer will just see the graph, will just see the plot, and then we make the estimation of the system in that case. Of course, there's a lot of working going on, but this is somehow the summaries that we have. So the first point is the main or the principal or the first step that we need to make more adoption into the systems of agrivoltaics is just to go for better accuracy into the light assessment. So this is the first point. After that, we can go for further details. So in that case, the comparison shows nice results, so a good acceptance in that case. So this is a first scenario. So we have been thinking in the past just to modeling the irradiance into the panel, but now we become a little bit more complex. So I think this first approach is quite acceptable. In that case, backward ray tracing fits for complex scenario, and then higher resolution maybe is not really needed in terms of the crops in that case, because maybe just try to simulate half centimeter doesn't make sense for a farm in that case. And the economical estimates rely on the model accuracy. So basically this work, or part of this work, was funding for the German Ministry of Research. And actually this is an open call for all collaborators. So we also have a network so that we want to exchange ideas, exchange information, exchange data. And part of the future work that we are also having, and I hope my sensors are not getting offline this week because I didn't check the data loggers during this week in the conference, but we have a lot of data, try to modulate this spatial and time resolution system, and this is basically part of my job. And if you want to keep in contact, so I will be more than happy to have contact with you and hear about your opinions and also look for possibilities of collaboration. It was my pleasure to be here, and then I will be more than happy to share some ideas and talk about it. Thank you so much.
Thank you, Hugo, and also thank to all the speakers for keeping on time. Great. Questions?
Hello, my name is Richmond from Fraunhofer EC. I'm trying to figure out how you connected the whole model to the economic angle, because it wasn't too clear for me. Maybe quickly explain it.
Maybe this is not the main goal for this part of the system, or this presentation already, and this is future work that I'm working on, because the productivity of the land can be measured regarding the light assessment. So the first step is what I'm doing right now in order to try to connect on the system. So this is not part of the presentation, but we also have demonstrators in this part of Germany when we try to validate these models against real crop production in that case, and then try to really make a metric. So right now it's called land equivalent radio. I'm still not sure if this is the correct or the more accurate metric by the moment, but this is the first point. The key message here is that if we want to look for productivity, first we have to go for a nice assessment of light and accurate and also simple as possible in that case. So if we are able to have a nice accuracy into the PV production, that this is part of the work of many in this conference, but also somehow in the crop production that is even more complex, because then we just have a really universe of crops over there. So then we can just make a more accuracy system, because at the end of the day, one of the main barriers to adoption of this kind of technologies to the farmers is that they are not well sure if they are going to produce more. And to be perfectly honest, what we can see right now is if you have a normal land and you put PV models, you will have more energy. Or if you put crops, you will have more crops, but not as you have in agrivoltaics. So it's important to try to get a balance, and this is part of the efforts that we are trying to do it. So actually, we'll be more than happy to exchange ideas about what we are working and future publications, hopefully.
We have time for one more short question and short answer. Then I'll do that. You mentioned about the accuracy that the farmer needs, and of course he's not working on the millimeter scale. But at one point when you're approaching your PV or the shadow of your PV, your yield will go down. Can you comment on that?
Yes, absolutely. So I think what is important in that moment is we don't have to go into the millimeter scale, but at least we have to provide tools that are able to give some planning, like in the picture number 1 in that case. So if we are able to provide accurate maps for the farmer, then they can say, okay, if I put my crops in this size of the system, then there will be a nice production in that section just for the design. Probably, at least in case of Europe, it's not the case of my home country in Costa Rica that there are small farmers, but here we are talking about hectares. So this part of the accuracy is something that we have to keep in mind. And if we are able to provide this kind of planning maps to them, that will be also a really useful combination. Of course, there's a lot of plenty of work going over there because this is the first step. Then the second step that I'm working right now is just to try to make a transposition model between the solar irradiance and then the PAR, because we have to make the proper conversion, but this is still working on it. So hopefully I can present some results later.
Yeah. So thank you. Thank you again.